Good morning, Auto 2. We're going to be talking about fuel systems, or introduction to fuel systems here today. What this will include is how we make gasoline and some things about combustion and different types of malfunctioning combustion. It'll be kind of a broad-ranging introductory lecture. So here we go. So first of all, we get gasoline and diesel from crude oil that comes out of the ground. We also get more than just that. We get natural gas and other things like that. So we say makes gasoline, diesel, liquefied petroleum gas, which is LPG, and other petroleum products, all kinds of stuff. Oil's been very, very interesting during the whole pandemic thing, because oil, when we went on break in March, had been, in the $50 area per 40-gallon barrel of light sweet crude being traded, around $50. It dropped all the way to a negative number, and then it's back up, I saw yesterday, to about $30 a barrel. So oil's been crazy, as a lot of things have been this time, in this time in life. So what we've got here is, it just says that, it gives you an idea with what's called a fractionating tower, how we break crude oil into all different kinds of components, and you can see those here. So we get mixtures of what they call semi-solids, liquids and gases. So when they put oil into a fractionating tower, they heat it up. The heavy stuff stays at the bottom, the lighter stuff up. So way up at the top is LPG. Way down at the bottom is things that we use for roofing and for roads and lubricating oils and waxes and polishes and things like that. So we get highly flammable hydrocarbons from crude oil. So about 12% hydrogen, about 82% carbon. But anyways, I'm just sort of interested in you understanding how we get fuels and things, and what other kinds of things come out of crude oil. So a refinery, and your notes can be pretty simple on this, but a refinery is going to convert crude oil into useful products through what's called a distillation process. And to distill, the way we distill crude oil is we have what's called a fractionating tower, where we're going to just heat it up, heat up the crude oil. And again, the lighter things will go up, the lighter parts will go up, and the heavier parts are down. So heavy fuel oil that's burned in ocean liners and things like that is down here at the bottom. Diesel oil is a little more refined. Kerosene is pretty similar to diesel and just slightly more refined. And then gasoline, or petrol as they call it in foreign nations, is a more refined fuel at the top. So in terms of cost, probably these higher, this is my educated assumption, that the higher you go in the fractionating tower, it's probably a little more cost involved, but that's not necessarily true. In terms of distillation, diesel fuel has more energy in it than a gallon of gasoline, though, so that's kind of interesting. This is just another picture of a fractionating tower and how they separate things into different parts as they heat it up. So let's talk a little bit about gasoline complete combustion. So we want to mix gasoline with the right amount of air, and at sea level, what we call the stoichiometric air-fuel ratio is approximately 14.7 parts of air by volume by weight to 1 part of fuel by weight. So obviously by weight, that's a tremendous amount of air to fuel. We call that the stoichiometric, or chemically correct, or ideal air-fuel ratio at sea level. So obviously combustion, when we burn air and fuel, we produce heat, and that heat is going to cause gases to expand, and that causes expansion, that expansion of gases causes pressure, and of course the pressure pushes the piston down on the power stroke of our 4-stroke cycle. I do want to remind you that I know I'm going quick as I go through this. You can slow the speed down on the YouTube video, or hit pause, or whatever you need to do as we go along, okay? So gasoline combustion looks typically like this, where we have air and fuel being compressed into a highly explosive mixture. We get a spark, and as we explode, expanding gases are going to force the piston down. So normal combustion, and again, we're talking about gasoline engines, we're not talking about diesels. A spark plug is going to ignite the A/F mixture. That's the air-fuel mixture, which again is around 15 to 1 or 14.7 to 1, ideally at sea level. It takes about 3/1000th of a second to ignite the air and fuel. Of course, that will depend on the RPM of the engine. And max cylinder pressure, like it says, is reached a few degrees after top dead center. TDC is top dead center on the power stroke. The faster we spin the engine, the earlier we have to cause the spark to occur, so we have more time when the piston's coming up for the explosion to be ready to push it down at the right time. Okay, so this is just showing normal combustion where you get a flame front beginning at the spark and burning across the combustion chamber. This would be a hemispherical combustion chamber design here, or what we call a Hemi. Really good design for power and really good for emissions. And most engines today use a modified version of this. I'm going to move the camera down so you can see that this Ford Duratec cylinder head has what we would call a modified Hemi. It's not a true hemispherical, but the valves are canted in right and left like a Hemi, and the spark plug is coming down the center like a Hemi. So it's kind of a modified hemispherical design, and everybody seems to have some sort of a version of a modified hemispherical design to affect the way combustion happens in the cylinder these days. This is just showing as normal combustion occurs, the flame front or the burning is going to proceed across the combustion chamber. And again, it says piston has reached TDC and the flame is shooting through the chamber, forming heat and expanding gases, and it's going to push that piston down. And that's all they're showing you here. So it's kind of belaboring the point, I know. Okay, let's keep going here. So our air fuel mixture that's ideal for making combustion produce as much power as we can, getting as best gas mileage as we can, and producing the least amount of emissions as we can is what we call our stoichiometric, which is another way of saying chemically correct or ideal air fuel mixture. And the ideal mixture, again, 14.7 parts of air to fuel at sea level. So there it is, as we've been saying, and by weight. Under constant operating conditions, the mixture burns all of the fuel. Now, that's not really the case. We don't burn all of the fuel. We always have some leftover hydrocarbons, and we have some other pollutants. So we'll talk about that here in just a moment, but that's pretty normal. So a lean air fuel mixture means we have a higher air to fuel ratio. So this might be like 15:1 or 16:1. I think it's on here. Let me see if it says. Nope, it doesn't. Okay, so let me go back. So higher air fuel ratio, so like a 15:1 or 16:1 is a leaner, that's more air to fuel. This gives you really good economy and mostly lower emissions, lower hydrocarbons, lower carbon monoxide, but you tend to get too lean and then hydrocarbons go back up, and you also make too much oxides of nitrogen, which is another pollutant. So too lean causes lack of power if it's too lean, misfire, and potentially can cause engine damage if it gets really lean, because when we're lean, the engine temperature goes up. More oxygen means more heat to a certain point, and that's going to melt things. So a rich air fuel mixture is more fuel to air mix, so like a 12:1, 13:1 ratio where you have less air to fuel. This tends to make more power, but it tends to give you worse gas mileage because you're consuming more fuel, and it tends to pollute more. Okay, so some pollution goes up when we're real lean, and some goes up when we're real rich, and kind of in between around that stoichiometric air fuel ratio is when emissions seems to be as minimal as we can make it. Overly rich reduces power and fouls spark plugs. That means that side to center terminal can get fuel soot on there, and then the spark starts jumping on the fuel and actually doesn't ignite it, and that will cause incomplete burning, and our check engine light will be on, etc. So let's talk a little bit about abnormal combustion. So when we say the flame or the flame front doesn't spread evenly and smoothly through the combustion chamber, and so here's our common types of abnormal combustion, and we're going to talk about each one in the ensuing slides. So if you don't write them down right here, that's fine. So common types of abnormal combustion are detonation, preignition, dieseling, and spark knock. Detonation, preignition, spark knock are real similar. They're just caused by different things. Some people call them pinging, but they're basically three different types of detonation is really what they are. So let's talk about them. So detonation causes engine knock or pinging by the collision of two flame fronts, and we're going to show this. Over time, damage will occur So here's a piston that burned a hole or beat a hole right in the top of the piston because it was detonating. And this engine was towing a horse trailer and was probably running 87 octane fuel, which is too low an octane of fuel and tends to knock more. And eventually it beat a hole in the top, and we'll talk about how that happens. So detonation is a secondary explosion. Sorry about the way this came up. That was kind of tricky. A secondary explosion that's going to cause engine knock and eventually cause damage to the engine. So detonation goes like this. We ignite the air and fuel with a spark, and it starts burning, okay? And then as it continues to burn across the flame front, watch what's going to happen here. We're going to get a secondary explosion here. And that secondary explosion and this explosion are going to cause a sonic shock. So you're going to have basically a sound wave hitting and a shock. And the consequences is it's going to rattle the piston back and forth and beat on it. And so there's a couple of different flame fronts colliding, if you will, and you get a big pressure spike. And this can be caused by low octane fuel, engine overheating, ignition timing improper, and things like that. We'll talk a little more in a moment here. So there's a spark plug that's been damaged by detonation with cracks, and the porcelain insulator is falling off. Okay. There's a piston that's just like the one I showed you, where you've had detonation beat a hole in the top of the piston. And that doesn't happen overnight. It takes time. You've got to really not pay attention to the way the engine sounds to get that to happen. Because we have knock sensors these days, hopefully this doesn't happen so much anymore. So let's talk about preignition. So preignition is a type of detonation. Preignition occurs because an overheated surface, like a piece of carbon in the combustion chamber, actually causes a secondary explosion. So this isn't caused by low octane fuel or something like this. This is caused by something inside the combustion chamber glowing, and it ignites the air and fuel. So a carbon particle, a sharp metal edge, or a hot exhaust valve, if the exhaust valve's not getting cooled like it should be, it's too hot, maybe because the air fuel mixture is a little bit lean. But typically preignition means something else is causing a secondary igniting of the air fuel mixture. And in all cases, whether it's regular detonation or preignition, you are going to hear a pinging noise unless you have a detonation sensor or a knock sensor, which is going to retard the timing, which will get rid of it, so you may not hear it. And if you're a teenager and your stereo is too loud, you're not going to hear it anyways, okay? All right. So here's preignition. Preignition means I ignite the spark, but I get a secondary explosion because there was a piece of carbon over here that caused it. The two flame fronts collide, rattle the piston, beat holes in the top of it, etc. So spark knock. Spark knock is another type of detonation. Spark knock occurs when the spark plug fires too early. So the piston's coming up, and instead of, let's say, at idle, or let's say at 3,000 RPM, the spark occurring at 45 degrees before top dead center, we start the spark at 55 degrees before top dead center. So as the piston's still coming up, the pressure rise is too much too early, and then the pressure rise causes a secondary explosion because the pressure has gone up so high, and the two flame fronts collide, and you hear the pinging where you damage the piston. So this happens because our spark timing, when the spark occurs in the cylinder, is too far advanced or too early in relationship to where the piston is. So max cylinder pressure occurs too early when the piston's still moving up, and then we get the flame front colliding. So maximum cylinder pressure gets too high too early, and so as the piston's coming, it's trying to push against combustion pressure, too much combustion pressure, and we rattle the piston. Okay. So spark knock causes pinging under load or knocking under load, and we're going to check the timing first and make sure it's not the cause, because it could be. If the timing's correct, we want to look for causes of preignition. But any car that does not have a distributor, which is everything for the last 25 years, pretty much, unless you're a Honda, 20 years, we can't set ignition timing anymore. So we usually don't go looking at timing it. We can plug in the scan tool and look at the ignition timing, but it's usually bouncing around because the computer's adjusting it. So we might want to look for causes of preignition, which means we may want to run some fuel injector cleaner through it to try and clean some of the carbon off the backs of the valves and the tops of the pistons. Okay, there's other ways we can do what's called an induction service, where we run a cleaner down through the intake manifold and hopefully clean off a lot of what's on top of the pistons. So spark knock is just showing the plug starts too early, the piston's too far down, the piston's still coming up, the pressurize is too great, and we get knocking. Okay, so it's just showing it, the pressure building, and then we get the secondary explosions as a result of that. So these are all different reasons for getting secondary explosions that we don't want. We want the flame to burn consistently and evenly across the top of the piston. Okay, so dieseling is essentially another type of detonation, but it's a detonation that occurs once I've turned the engine off. So I shut the engine off and the engine basically keeps running, and it sputters and knocks and finally gasps and shuts off. It's not, this happens on gasoline engine. It's a little bit confusing when we call it dieseling. The true name of it is run-on, engine run-on. That's the accurate name, but most everybody calls it dieseling. And it's mostly an old school carbureted car phenomena. We don't have this on injected cars anymore because when we shut the ignition off, we're turning the fuel pump off, so no fuel can be sprayed in, so the car can't run. If I have a leaking injector on an injected car, then the car can actually keep running. But it used to happen on carbureted cars a fair amount. We would get coughing, knocking, and all kinds of weird noises as the fuel ignites and the crankshaft turns. So I shut it off and it and it keeps going, and finally it shuts off. Many times it's in the crankshaft will spin backwards when it finally shuts off. So gasoline is ignited by heat and pressure in the cylinder. Mostly if I have a carburetor and the throttle plate the idle speed's a little too high, throttle plate's open a little more than it should be, I shut the engine off, and as the pistons are slowing down, the vacuum is still sucking, the descending motion of the piston causing vacuum is still sucking fuel past the throttle plate, and you've got fuel and there's still air there, it'll still try and fire. So a high idle speed or too much idle speed typically causes this, engine overheating, a few other things like that. So I think it's going to say what they are. So common causes: high idle speed, carbon deposits in the combustion chamber, so there's still something glowing to ignite some air and fuel in the cylinder, even though I've shut the spark down or shut the coils down. Low octane fuel can cause it. Engine overheating should come up, yeah. Engine overheating, and then spark plug heat range too hot. Don't worry about this one, that's kind of an old school thing. But low octane fuel, engine overheating, high out of speed. But again, it's a carbureted car problem almost exclusively. Unless we have an injector that's leaking, then it's possible this could happen. But this is an old school kind of problem, engine run-on. So there's our little lecture on an introduction to fuel systems. And I hope you took notes, and that'll add to your note sheet. And we'll talk to you soon.